Good morning, children. I hope you're all doing good. So far in our classes, we have discussed about patterns, different types of patterns, in particular arithmetic and geometry sequences. Today's lesson, we are going to talk about something called as arithmetic series. All right, let's kick it. First, we'll just introduce what is series and how to understand what is an arithmetic series. And then we will just revisit how Gauss calculated the sum of first 100 natural numbers. At this juncture, I would like to reiterate that you should have watched the video posted in ManageBack. If not, please pause this, go back and watch the video, and then come back to this video. Later, we will add a new perspective to derive the general formula to calculate the sum of a arithmetic series. And then using that formula, we will have some problem solving, and then we will leave you with some interesting questions that we would like you to research upon, and we hope that it will be an enjoyable experience. What is a series? Series is nothing but if you add together the terms in the sequence, we call it as series. Hmm, not that difficult to understand, is it? Okay, let's look at an example. 7, 11, 15, and so on. You might have already identified a pattern going on here, isn't it? That's nothing but an arithmetic sequence. It doesn't matter. It can be any sequence for that matter. If you put all these terms in the form of an addition, then it becomes a series. I think I wrote 5 by mistake. Let me correct it. It is 7, 11, and 15. It keeps going and going. So this is what we call as a series, and sum of the series is nothing but it give you one particular value. This is just going to give me a one particular value. We are going to discuss how do I find that, in what context it is good to find, and different other questions that we are going to go through. Before that, let's go back to what is an arithmetic series. Well, if series is nothing but the sum of the terms in a sequence, then arithmetic series is sum of the terms in a arithmetic sequence. Okay, let's take another example where I have arithmetic sequence and the corresponding arithmetic series. Uh-huh. 3, 5, 7, 9. Yes, you guessed it right. The common difference in this case is 2. How do I get the corresponding arithmetic series? Not so difficult. You just get rid of this comma here, replace it with the plus operation, addition. Okay, now let's look at one more example. 2, 4, 6, 8, 10. Again, the common difference is 2. In this case, the corresponding arithmetic series would be 2, 4, 6, 8. 2 plus 4 plus 6 plus 8 plus 10. Not so difficult to calculate this, right? Okay. Now, I would like you to think about, is there a difference? Is there a particular thing that you can consider with respect to these two examples? You may pause the video if you have to. Yes, I would like you to look at the number of terms in the sequences, in these two sequences. How many terms are there? Well, it keeps growing, right? And therefore, it has infinitely many sequence. And corresponding to that, whatever series I'm going to write, whatever arithmetic series I'm going to get, it will also have infinite number of terms. Therefore, it's an infinite series. Now you would have already guessed what about the second guy. That is nothing but a finite sequence. It ends at some point. We can easily calculate and tell you how many terms are there in that particular sequence. That's what we call it as a finite sequence. Similarly, I can say that this guy 2 plus 4 plus 6 plus 8 plus 10 is nothing but a finite series. It is a little bit important at this juncture to know why I have to talk about the number of terms. As long as I have a series, I can just keep calculating. Well, that is not so interesting. Well, if I give you infinitely many terms, you will end up in something called as infinity. Yes, you heard me right. If you add infinitely many terms in this fashion, right, you're gonna get infinity because it keeps growing. In this case, it keeps getting bigger and bigger by 2. Is it only in this case I will end up with infinity? Why is it? What will happen if I start with something, let's say 7, and I decrease a value? So I get a sequence like 7, 6, 5, and so on. Again, this is also an example for arithmetic sequence with common difference being 1. In this case, the series would become 7 plus 6 plus 5 and so on and so forth. As you move towards the left side in the number line, you see that you're going to add more and more negative numbers, and eventually, where will you land? Yes, that's where you will land at negative infinity. So either it is increasing or it is decreasing. It's not so interesting. I already know the answer. What I do not know is how do I calculate the sum of a finite arithmetic series without having to calculate the value term by term. Is there a rule? Is there a formula that I can use so that I can get the answer instantaneously? So that's what we are going to learn about, and that is also very important because it is part of something called as counting, and in mathematics counting plays a very, very vital role. Hmm. Yes, there are so many people who have talked about counting, and there are so many quotes that have been put up. And one of my favorite memes, or you can call it a joke, is this one. There are three kinds of people: those who can count and those who can't. If you did not laugh, you should pause and realize what is the joke here. Going, okay. Yes, as I mentioned towards the beginning of the session, you should watch the video that was posted in ManageBack. It talks about how, as a young child, Gauss calculated the sum of first 100 natural numbers. He was given the task by his teacher to calculate, to add all the values from 1 until 100, and he did it with ease. So he used the technique in the video. It was mentioned like he used the technique something like you got a pattern where you have a triangle, and then he divided the triangle equally, and then he put this part over here to form a rectangle. Well, that is one perspective. Actually, there is another side of the story. That's what we are going to see next. Some people believe that this is how Gauss did it. How did he do it? First, he wrote all the numbers from 1 to 100 in the addition format, in the series format, from left to right. And then, interestingly, he thought about it for a moment and wrote all the way from right to the left. He wrote it in the reverse direction. Now, this is my first equation and this is my second equation. Both are exactly the same, but I want the answer for only one of them. But what did Gauss do? He added them. That means he is going to get twice the amount what he actually wanted. And interestingly, you can see a pattern that turns up here. Each of these corresponding terms in these equations always gives you a value of 100. How many such 101s I have? The number of terms I have in this series, the number of 101s I have, which is nothing but 100. Therefore, I can say that my twice the amount of S is nothing but 100 times 101. However, we know that I want only one sum. Therefore, you just divide it by 2. Interesting, isn't it? This is another way that Gauss could have calculated. So all these are based on the stories. Now let us think if this method works for any type of arithmetic series that is given to you. So let us try to see one more example to understand it. Look at this arithmetic series: 71 plus 69 plus 67 and all the way until negative 27. Yes, you should have realized that it stopped at negative 27. Therefore, it is a finite arithmetic series. Okay, so you first write from the left to the right and then you write it backwards. And then what did you do? You just add them together to get twice the amount of what you want. Okay, in this scenario, each of the terms gives rise to a value of 44. And how many such 44s are there? The number of terms that you have used in this particular series. And how many such terms are there? There are 50 such terms. I think I would recommend you to pause the video if you are not able to calculate how you got 50 over. And then we can just say take one corresponding term here. For simplicity, I'm just going to use the first term and the nth term or the last term. So 71 and negative 27. Therefore, I can calculate the sum of this particular finite arithmetic series. Well, the trick seems to work for others series which doesn't start with 1 as well, isn't it? Now let's try to do the general approach. What is the general approach? I'm going to use the general sequence and convert into general arithmetic sequence and write the general arithmetic series version of it. A1 plus A1 plus D, which is nothing but the second term of a arithmetic sequence. So A2, that's how we used to denote it, right? A3 and so on. And the last term or the nth term, we call it AN. Okay. Now, what is the next step? The same thing, I want to write it in the reverse direction, right to left. Okay. Next, yes, you guessed it right. I have to add each of these terms in a corresponding fashion. Okay. What do you think you would get? Well, this is the first term in first expression, and this is the first term in the second expression. When I add these two, I'm going to write it as a1 plus a1. My bad, sorry. This should be a1 plus n minus 1 into d. Okay, let's see if I can get something very similar when I add the second term on these two expressions, which is given by these two terms. All right, so a1 plus d, and then here it is a1 plus n minus 2 times d. When I add these two, I'm going to get a1 plus a1 plus d plus n minus 2d. Now I can just simplify this with respect to d. So a1 plus a1. Why I did not combine this? I can see that I want something very similar to this term. So I'm just gonna simplify d. When I take d as a common factor, this is going to be 1 plus n minus 2. 1 plus n minus 2, which is nothing but n minus 1. Hooray! Yes, I see that I'm getting the same value as exactly as the first terms in these two corresponding expressions. So similarly, you will see that if you calculate it manually, every corresponding term in these two expressions will end up with you will lead you to the term a1 plus n minus 1 into d. Therefore, I can see that this is what is happening, isn't it? And you can realize that a1 plus n minus 1 times d is something very familiar. It is nothing but my nth term. Okay, let me get rid of this so that you can see it very clearly. Yes, now you can see that each of these terms contains first term as well as the nth term. Therefore, what do you see? And how many such terms are there? There are n such terms are there. And what did I do? I just added the first term with the nth term. Okay, so therefore I can get my sum of first n terms of a arithmetic series. So we use the symbol Sn to denote the sum, and these other notations are very familiar to you. Now, there can be two different formulas given for an arithmetic sum of an arithmetic series. One is just what we have seen. Some places occasionally what they have done is they can still expand this an in the form as a1 plus n minus 1 into d, and if you substitute this value into this equation, you will get a1 and a1 repeated here twice. Therefore, I can simplify this and write it as n over 2, 2 times of a1 plus n minus 1 times d. I'm plugging this value for an in this equation to get this. Well, why is this even necessary? Okay, it can be quite handy in cases where you do not know what is your nth term. However, you know your first term, which is a1, you know your common difference, and you know your number of terms in the sequence. Well, it can be easily obtained just by finding the nth term also. Yes, but for simplicity, some authors use this formula for that purpose. So if you are given the nth term, you can directly use this. If you are not given the nth term, you are only given n and the first term and the common difference. You can either use this formula directly, or you can find the nth term first and then plug into this particular e formula. Okay, let's go ahead and see some examples now. The first example talks about calculating the sum of the first 63 terms of this particular arithmetic sequence. Yes. So as you can see, I have all my variables that I want here that I need to plug into my formula, which is Sn equal to n by 2 into a1 plus an. Did you recognize that? I do not have my nth term. Yes, that's what I'm going to do first. So in order to use this formula, I know that my a1 is negative 19 and my n, which is given in the question, is 63. However, I first have to calculate my an, or you can alternatively plug into the second formula that we derived in the previous slide. Okay, to calculate an, I'm going to just follow the normal process how I did problems in arithmetic sequence. So finding an, plugging in these values here, and then I can plug the value of an that I've obtained into this formula to get the sum of first 63 terms of an arithmetic series. Okay, let's look at the next example. So here I want to calculate the sum of the sequence. Now you see that you are given the nth term. Okay, they did not specify what type of sequence is this. It is very important that you need to understand what type of sequence before you even calculating the sum of the series. As you can see, the common difference is being maintained, which is negative 5 in this case. Therefore, I don't have to worry. It is a arithmetic sequence. Therefore, I can use the formula for arithmetic series, which is Sn equals to n over 2 times a1 plus an. I know my an, which is negative 38. I know my a1. Okay, I also know my common difference. But what is missing? N. Again, we'll use the knowledge of our arithmetic sequence to calculate n using an. So just plug in the values here, and then you see that my value of n is 12. Once I know my value of n, I can just plug in all these values in this particular equation, and you're done. There you go. Hmm. Does this look familiar? Yes, it should, because it was from your background knowledge document. Yes. So now that you are equipped with the necessary skills to deal with problems that involve arithmetic sequence and arithmetic series, why don't you go ahead and give it a try? Yes, you should, right? Don't worry if you're not able to do it, we will still discuss in class. As I mentioned earlier, there are something that are interesting and challenging awaits your away. So the one that we calculated earlier, sum of the first 100 natural numbers can be generalized as sum of any first n natural numbers. And using the formula that we have learned, it is very easy to say that 1 plus 2 plus 3 all the way until n can be derived as n over 2 times n plus 1. Now, okay, this is a famous formula which we call it as sum of the first n natural numbers. And what will happen if you square each of the terms in the sequence and then add them together? Think about it. Just take some small values for n, let's say for 5 or 6, and then try to see if you get a pattern. What about if you cube them? Well, that sounds more interesting. And you can keep on repeating this process. You can take to the power 4 and so on and so forth. But there is something else we would like you to research upon. Try to identify the patterns, right? Is there a relationship between the answer that you are getting in each of these three terms? The linear series, the quadratic series, the cubic series. Okay, so just think about it, give your best, and then we will see you later in the class. That's all for now. Thank you.